Swayam Prabha. Digital India. Educated India.
Hello, welcome back. So in this second part of this lecture, we'll be covering the topic of Smith chart. So what is this Smith chart? So Smith chart, the concept of Smith charts with what we call a bilinear transformation. So what is this bilinear transformation? So it is given like this. So this here, this is the gamma plane. This gamma, capital gamma, represents the gamma plane. Z0 is just a constant and Z is the impedance. Now you might find this equation is very similar to the definition of reflection coefficient that we have come across just a few in the previous part. Actually, that is not the intention, though the two forms coincide. So right now, for now, assume that this is just a bilinear transformation. We are just performing a mathematical coordinate transformation. But yes, that's also true. Ultimately, what happens is Z impedance is transformed from the impedance domain to the reflection coefficient domain. Okay. Now these quantities, this Z upon Z0 and Z upon Z0, can be replaced by what are known as normalized impedance. And this Z is given by so what how does this transformation work then? Now what happens is, suppose we plot a series of lines like this in the Z plane. Okay. Now say this horizontal line represents R equal to 1. This represents 0.5. This represents 0. This represents minus 0.5. And this represents minus 1. Similarly, say this line represents, so this is x. Okay, so this is x equal to 0. This is x equal to 0.5, and this is equal to 1. So what this bilinear transformation does is it transforms these horizontal green lines. Okay. Now just a small correction. These are not. These are R is given by this, and X is given like this. Small correction. So these green horizontal lines represent constant reactance. Similarly, this vertical lines represent constant resistance. Okay, so these constant resistance lines, how do they get transformed? They get transformed like this. Excuse my handwriting, but these green and red lines both are supposed to be circles. So the previous one was the Z plane. This is the gamma plane. Okay, and this is the from a say x from a r equal to 0.5 straight line. This one that has transformed to this. It's a r equal to 0.5 circle. Similarly, this is r equal to 0 circle. This is r equal to 1 circle. And these green lines, this is the x equal to 1. So this one is x equal to 1 constant reactance circle. So what basically has happened is that this green line has become this one. Similarly, this is the x equal to 0.5 constant reactance circle. So this has become this. Okay, this is the x equal to minus 0.5 constant reactance circle. So this line has become this. Then this is the x equal to minus 1 constant reactance circle. So this has become this, and so on. So that's how this this happens. Okay, so for example, we can have we can have various interesting cases like what happens to the x-axis. So the x-axis, which is this one, which is basically a constant reactance line here, this one. How does this get transformed? So the x-axis gets transformed. See, the x-axis is between the x equal to 0.5 circle, this line, and the x equal to minus 0.5 line. So it must be somewhere between this line and this circle and this circle. And actually it is the x-axis. So it is like a circle which has infinite radius, and this x-axis basically forms a part of the circumference of that infinitely large circle. Now here I would like you to go through the derivations of these circles. These are given in the book by Gonzalez or even in Posar. So the exact equations for these circles, please go through it once. So this is our gamma plane, okay, whereas this is our z plane, okay. So hope this is clear. Now we can, one thing to note is, let me redraw the Smith chart. So this particular diagram with this circle having radius of 1, this outer circle, so this point is actually 1, minus 1, minus 1, 0. This point is 1, 0. So this circle, which has a radius of 1 units and which has a center at the origin, is called the, is basically defines what is the Smith chart. So in a Smith chart, you will have constant resistance circles and constant reactance circles. And because these reactance and resistances are normalized, so it doesn't, the absolute values don't matter. Okay, so the normalization procedure I have shown how this was like this. So say there is a particular point. So we shall see how to locate the particular points on that. But say, just to give you an example, say we have this point, okay, this point. Now this is here resistance R equal to 1 and X equal to 0.5, right? This is that point on the Z plane. What is this corresponding point on the Smith chart? So first we locate the R equal to 1 circle. So this is the one, this one, okay. And where is next is the X equal to 0.5 circle. So this is the one. The intersection of the two is the 1 comma 0.5 point, okay. So this is how we locate, this is how points get. So this point is translated to this point in the Smith chart. Now the Smith charts are available online, you can go through them. Let us discuss some of the properties of the Smith chart. One is the first important property to note about Smith chart is that, so this is our Smith chart, okay. So we can again draw the points. So all points inside the Smith chart correspond to passive devices. Okay. So this is the boundary of this outer circle is the boundary. Again, on the gamma plane, this point corresponds to minus 1, 0. This point corresponds to 1, 0. So all points within this unit circle. So I shall be calling this circle the unit circle. This one. Okay. All points within the unit circle correspond to passive impedances, and all points outside this circle correspond to active. You can check that out. Okay, so all passive devices are inside the Smith chart. All, I beg your pardon, all passive devices can be considered to have impedances or reflection coefficients which lie inside the unit circle, and all active devices will have reflection coefficients which lie outside the unit circle. Okay, so that is one advantage of the Smith chart, because all passive devices, whatever be their impedances, we can view it within this unit circle. So that makes it easier as compared to, say, the Z plane. If I plot the Z plane, okay, it is like this. So in the Z plane, the passive devices are those occupy that portion. The impedances of passive devices occupies that portion of the Z plane where R is greater than 0. So that means the entire right half of the Z plane, isn't it? This is the passive region, and this is the active region. Or by active region I mean the region which corresponds the region in the Z plane where the impedances correspond to active devices, because here R is lesser than 0. So these active and passive devices, so this entire right half of the S plane of the Z plane, this entire right half is coordinate transformed to the inside of the unit circle on the gamma plane. The advantage of this operation is that it helps us visualize all passive devices within a limited region. Whereas on the Z plane, all the region occupied by passive devices is infinite, right? So that makes it difficult to visualize all impedances. Whereas here, we have now put all the impedances of passive devices at a single place, everywhere, whether it's infinite, then also it's here. Whether it's 0, that is also here. This unit circle acts as a boundary between the point where R transforms from greater than 0. So within this circle, R is greater than 0. Outside this circle, it is lesser than 0. Okay, so I can make that here also. So here R is lesser than 0 and R is greater than 0. Okay, so that is one big advantage. Now, if we consider a simple inductance, say a simple series inductor, okay. So if I draw the Smith chart, okay, and so this is the x-axis. So this is my unit circle. Say at omega equal to 0. So what is the impedance offered by this inductance? Suppose the value is L. The magnitude of the inductance of the impedance offered by this series inductor will be purely imaginary. Not the magnitude, the impedance offered will be purely imaginary, and its magnitude is given by omega L. So at omega equal to 0, okay, the value will be x will be equal to 0, right? So what point on the Smith chart corresponds to x equal to 0 and also R is equal to 0, because there is no series resistance connected here, connected to this inductor. So let's see. So this is our R equal to 0 circle, right? And as I said before, the x-axis forms the x equal to 0 constant reactance circle. So then this point should correspond to these values. Okay, so when omega equal to 0, this is the value. Now, as omega increases, the value of r continues to be 0, but x continues to increase. So which means that the locus that will be followed for omega increasing will be along the circumference of this circle. Okay, so it will be like this. It will be like this. This is the locus that will be followed. And then when omega becomes infinity, we will reach this point. Omega reaching infinity means the value of this reactance also becomes infinity, which in turn means that for very high impedance or infinite impedance or very high value of x, we will reach this point. So this point must then correspond to open. Similarly, for very low frequency, omega, the reactance will be 0, so this becomes a short. So this point corresponds to short. So on a Z Smith chart, this is called a Z Smith chart, or the entire Smith chart theory that we discussed just now is what is known as a Z Smith. Why? Because we use this relationship, right? So here our parameter, which is translated to the gamma plane, is impedance or the normalized impedance, this one. But as we shall see, Y Smith charts are also possible. That is, we can have another type of Smith chart. It's called a gamma dash, where our starting point is the normalized admittance instead of the normalized impedance. Okay, so fine. Now let us see what happens if we have a series capacitor. So a series capacitor is like this. The magnitude of the reactance offered by this capacitor is given like this. So once again, if we draw our Smith chart, okay, so at omega equal to 0, the reactance is infinity. So r equal to 0, x equal to infinity, which point is it? So see, one thing we have to understand, as x, so for x, this is our x equal to 0 constant reactance line. This is our x equal to 1 constant reactance line. So as what we see is that as the reactance value keeps on increasing, all the circles keep touching this point. Constant reactance circles keep touching this point, but their radius decreases. So in the extreme case, when x is equal to infinity, the circles will go like this, like this, like this, and then when x equal to infinity, it will become a point. So this point corresponds to r equal to 0, because this is the r equal to 0 circle still, and x equal to infinity. So at omega equal to 0, we start from here, and this is still the open. As omega keeps on increasing, the value of the reactance decreases, and if the value of the reactance decreases, then the radius of the circles keep on increasing, right? Like this. So the locus that is then followed by the, as the omega locus that is followed by the reactance as the value of omega increases, I beg your pardon, is this one. So it goes all the way. So at omega equal to 0, we start from here and we reach this point at omega equal to infinity. So it is kind of like the opposite of what happened for this inductance, this one. So while for the inductance we started from here and went here like this, for the capacitance we followed the bottom half, followed the circumference of the lower hemisphere. Okay, one important parameter that is frequently we come across, which is sort of like an alternative definition for impedance or reflection coefficient, is what is known as voltage standing wave ratio. Let me use a fresh page. So if we define the reflection coefficient like this, then we know, suppose again we have a transmission line, say at a distance x on the source. Say the total length of the transmission line is L. Then V of x, as we know, will be given by this relation. Now the maximum value of V of x will be given by, so the maximum value happens when this phase 2 beta x equal to 2 pi, so that these two terms, this term and this term, just add up, and the value will be given by 1 plus V minus upon V plus, and this we can write as 1 plus the magnitude of the reflection coefficient at this point. Okay. Similarly, the minimum value of this voltage is given by now the ratio of this maximum value and minimum value is called VSWR. So VSWR is defined simply as this. That's the definition of VSWR.